Imagine a power source so immense, so fundamental, it could redefine civilization. We're talking about harnessing the universe's ultimate engines, black holes. This isn't science fiction. It's a frontier for the boldest tech innovators, exploring the theoretical possibility of extracting energy from these cosmic behemoths. Our planet's energy demands are ever-growing, pushing the boundaries of conventional sources. For centuries, humanity has sought more efficient and powerful ways to fuel progress. Now, we look beyond stars, towards the most extreme gravitational phenomena known. Black holes represent an untapped reservoir of energy, far exceeding anything we currently comprehend. Their immense gravitational fields and unique quantum properties offer pathways to power generation that could sustain interstellar civilizations. This pursuit challenges our understanding of physics and engineering. The Penrose process, proposed by Sir Roger Penrose in 1969, offers a fascinating theoretical pathway. It suggests that energy can be extracted from a rotating black hole by exploiting its ergosphere. This region outside the event horizon is where space-time itself is dragged along with the black hole's rotation. Within the ergosphere, an object can momentarily possess negative energy relative to an observer at infinity. This counterintuitive concept is a direct consequence of general relativity. It opens the door to a unique energy extraction mechanism. The core mechanism involves injecting a particle into the ergosphere, where it splits into two fragments. One fragment, carrying negative energy, falls into the black hole. The other fragment is ejected, having gained energy from the black hole's rotation. This energy gain is not from the particle's mass, but from the black hole's rotational kinetic energy. This process effectively slows down the black hole's spin, converting its rotational energy into usable kinetic energy for the ejected particle. It's a cosmic dynamo, transforming the black hole's angular momentum into a tangible energy output. The implications for future power generation are profound. The maximum theoretical energy extraction efficiency for an uncharged black hole via the Penrose process is about 20.7% of the mass of the injected particle. This efficiency is achieved when the particle falls into the black hole with the maximum possible negative energy. It represents a significant energy yield from a purely gravitational interaction. However, some researchers estimate that the process could achieve efficiencies exceeding 100%, even up to 150%. This superradiance occurs when the incident wave or particle amplifies upon reflection from the black hole. This amplification is possible because the black hole effectively leaks energy, which is given away for free to the plasma escaping from its vicinity. In 2020, the Penrose process was experimentally verified using an analog system. Researchers used a rotating sound absorber to mimic a black hole's ergosphere, demonstrating the superradiant scattering of sound waves. This groundbreaking experiment provided tangible evidence for a phenomenon previously confined to theoretical physics. While an analog experiment doesn't directly translate to real black holes, it validates the underlying physical principles. For tech innovators, this means the theoretical framework is robust. The next steps involve conceptualizing how to scale these principles to astrophysical scales, addressing the immense engineering challenges. In 1974, Stephen Hawking proposed another revolutionary concept. Black holes emit radiation due to quantum effects near the event horizon. This phenomenon, known as Hawking radiation, fundamentally changes our understanding of black holes. It suggests they are not entirely black, but slowly radiate energy. This radiation arises from the bizarre world of quantum vacuum fluctuations. Particle-antiparticle pairs are constantly popping into and out of existence everywhere in space. Near the extreme gravitational gradients of a black hole, these fluctuations take on a new significance. Near the event horizon, one particle from a virtual pair might fall into the black hole, while its partner escapes to infinity. The particle that escapes carries positive energy, appearing as emitted radiation. The particle that falls in effectively carries negative energy, reducing the black hole's mass. This continuous emission of particles means black holes are not stable, eternal objects. They slowly lose mass and energy over time. This process is incredibly slow for stellar mass black holes, but it becomes significant for smaller, theoretical black holes. Hawking radiation leads to black hole evaporation, where the black hole loses mass and energy over time. Smaller black holes are predicted to radiate more intensely and evaporate faster. A black hole with the mass of a mountain, for instance, would evaporate in a matter of seconds, releasing an enormous burst of energy. Theoretically, Hawking radiation could be harnessed as an energy source, especially from these smaller primordial black holes. While the radiation from stellar black holes is incredibly weak, far too faint to be useful, the intense emission from micro-black holes presents a tantalizing possibility. This concept pushes the boundaries of energy density. The challenge for tech innovators lies in creating and containing such micro-black holes. If we could synthesize and stabilize them, their Hawking radiation could provide an unparalleled energy source. This would require unimaginable energy densities for creation and advanced containment fields. The energy output from a micro-black hole could be immense, potentially powering entire cities or even interstellar spacecraft. This vision requires breakthroughs in particle accelerators, magnetic confinement, and exotic matter manipulation. It's a grand engineering challenge for the 22nd century and beyond. While the theoretical foundations are compelling, transforming black hole energy into a practical reality faces monumental challenges. These aren't just engineering hurdles, they are fundamental physics and materials science problems that demand radical innovation. For tech innovators, these challenges represent the ultimate proving ground. Reaching a black hole, especially a stellar mass one, is an interstellar journey of immense scale. Even if we could reach one, the extreme gravitational forces and radiation environments pose insurmountable challenges for current technology. Developing propulsion systems capable of such journeys and materials resistant to such forces is a prerequisite. Furthermore, converting the extracted energy into usable forms requires entirely new paradigms. How do you capture and transmit energy from an ergosphere or from evaporating micro-black holes? This demands breakthroughs in energy conversion, transmission, and storage technologies. The Penrose process, while theoretically efficient, still requires precise particle injection and retrieval in an extreme environment. The energy yield, while significant, must be weighed against the immense energy input required to initiate and sustain the process. Optimizing this energy balance is crucial for viability. Hawking radiation, while powerful from micro-black holes, is incredibly faint for larger ones. This means we either need to create and manage micro-black holes, which is currently beyond our capabilities, or find ways to amplify the incredibly weak signals from larger ones. Both paths require revolutionary scientific and engineering advancements. Creating and maintaining small black holes for energy generation would require technology far beyond our current understanding. The energy required to compress matter into a black hole is astronomical. Furthermore, preventing their rapid evaporation, or controlling their evaporation rate, would necessitate advanced containment fields and a continuous supply of matter. This challenge touches upon fundamental physics, how to manipulate space-time and gravity on a macroscopic scale. It demands breakthroughs in high-energy physics, quantum gravity, and potentially exotic matter. This is the ultimate test for materials science and energy manipulation. Beyond Penrose and Hawking, Other theoretical methods for extracting energy from black holes exist. These include harnessing the immense magnetic fields that often surround rotating black holes, or exploiting the properties of plasma accretion disks. These alternative approaches offer different avenues for innovation. Research into these areas is ongoing, pushing the boundaries of theoretical physics and astrophysics. For tech innovators, this means a fertile ground for new ideas, interdisciplinary collaboration, and the development of entirely new fields of engineering. The future of energy may lie in these cosmic powerhouses. The concept of black hole power stations is a grand vision, a testament to humanity's insatiable drive to understand and harness the universe. It demands radical thinking, interdisciplinary collaboration, and a willingness to challenge established norms. This is not just about energy, it's about pushing the very limits of what's possible. To the tech innovators, engineers, and scientists of tomorrow, dive into the fundamental physics of gravity and quantum mechanics. Explore advanced materials capable of withstanding extreme environments. Develop computational models for complex gravitational systems. Your ingenuity will unlock the universe's ultimate power source. Join us in shaping a future where energy is limitless and humanity's reach extends across the cosmos. Hey, if you're enjoying this video and want to see more like it, don't forget to hit subscribe and turn on the notification bell so you never miss an update.